Okay, good morning, everybody. Today I have a great pleasure of introducing to you Dr. Alex Simpson. She's currently a research civil engineer at the U.S. Army Corps, based at the Field Research Facility in Duck, North Carolina. She recently completed a postdoc at Scripps Institute of Oceanography, working with Dr. Sarah Giddens and Dr. Alex Honor Devine at UW, and they were looking at small river plumes and how they interacting with the adjacent water system in the South Zone. And she comes with a PhD and a master's degree from Oregon State University in coastal engineering. She worked with Dr. Mary Carla, and she has a bachelor's from the ocean science, or bachelor's in ocean sciences from Cornell. So she has a very interesting research focus, um, looking at frontal features and how density fronts interact, maybe with the internal waves, and she's using all these fancy equipment, and I would like to hear more about that. I can't wait. So welcome, Dr. Simpson, to Stony.
Thank you. I appreciate it. I am coming to you from Duck, North Carolina. I think it's probably backlit, but the Duck Pier is out my window. So maybe some of you have been here and done work before here, but I'm going to be presenting on work that I did for my postdoc at Scripps. So I finished this position about 2 months ago, and we're kind of wrapping up the paper from this work. And a lot of my focus throughout, my early career so far has been using remote sensing technologies. So sort of my position on this project was leading remote sensing efforts. So a lot of sort of the technologies you'll hear tied into this talk are all, drone-based operations. So yeah, why don't I dive in? So I'm going to mostly focus on a project that it was an NSF project funded with PIs Sarah Giddings and Alex Horner Devine. And this was a large field campaign that we conducted this past, I guess, a year ago now in February. And this was conducted in an estuary that you see in this photo. This is just north of Scripps Institution of Oceanography. It's located within Torrey Pines State Park. This is called Los Penasquitos Lagoon. You can see, a river has sort of, I should say a very small river has entered into this lagoon region, which then outflows into the coastal ocean. And this is Torrey Pines State Beach. And the field campaign, the goal of this project is to study the interaction between the small river plume that discharges out of this lagoon, the interaction of that with the surf zone. So why do we study small river plumes? Well, despite being pretty prevalent around the world, our understanding of small river plumes is poorly understood. A lot of work has been done in sort of larger, more canonical, larger rivers, but even then still, our understanding of frontal interactions with waves is still pretty limited. And this type of system is quite important because these plumes can carry pollutants out into the near shore. They can facilitate in the exchange of sediment, so they can have implications in coastal erosion or accretion. Also, there's environmental impacts to the local biology with exchange of nutrients and larvae. So I want to just quickly add the definition here that, as I said, we're looking at small river plumes. So these are systems that typically have very low discharge, so less than like 100 cubic meters a second. And they're also small enough to not be affected by Coriolis. And just a kind of a comment about their prevalence. So as you see, I have my slide titled here, Intermittently Closed Estuaries. The system that we're studying falls under this category of low inflow estuaries that intermittently close off to the near shore. So in certain times of the year, such as the summer months, the outflow from the estuary gets so low that sediment actually backfills in at the mouth, and there's no longer any exchange between the river mouth and the near shore. And these types of systems are common, they're pretty prevalent worldwide. You can see sort of locations throughout the world, mostly in Mediterranean climates. And there are predictions saying that they will have lots of habitat loss due to sea level rise, and can also play important roles in sort of morphology that can influence effects of sea level rise and things like that. So I wanted to show just a few examples of plumes from our estuary. So these are 3 different snapshots that I've taken from planet imagery. This is satellite data just showing RGB imagery, just to kind of get a sense of the variability of what we're discussing when we say plume. So here we have the estuary mouth entering into the surf zone. On the furthest left image, we have what can be distinguished as a sediment plume. So we see a darkness associated with the sedimenty water that's coming out, but we also have a bunch of rip current activity. It appears we have these, plumes all along the coast. In the figure in the middle, here is a really nice plume with a foam edge to it that looks like it's pulsed out and gotten carried to the south. And this plume is distinguishable from sort of other nearshore plumes. And then on the furthest right, it's quite difficult to distinguish between river plume and surrounding rip current. So you can see this sort of nice mushroom head that looks like it might be more of a rip current than an actual plume ejection. So these are all examples of what a plume might look like in the instance that it makes it out onto the inner shelf. So you're going to see this slide come up a few times during the talk. I'm going to present us with a schematic for describing the system. So we have a coastline, we have a river channel entering into the coastline. The dashed line is the edge of the surf zone. Some factors happening at the edge of the surf zone, right? We might have ejections due to rip currents, so transient and or bathymetric rip currents. We also have the tide moving that surf zone in and out. We have waves that are impacting this region. And then the river plume discharges and will either sort of create this plume, or it might spread in the alongshore. So we have fresh water coming out of the river channel and either creating a plume or spreading in the alongshore. So to present our hypotheses for this work, our first hypothesis is that a river plume will escape the surf zone or punch its way out of the surf zone when that river momentum flux exceeds the wave momentum flux. So if there's enough momentum, it can make its way out. And if not, then that water will get trapped by the wave momentum in the surf zone. Our second hypothesis with this work is that we will be able to parameterize the conditions that lead to escaping versus trapping. And our group is making comparisons to 2 other similar systems, the Maipo River in Chile and the Quinault River in Washington. The third hypothesis is that if that river plume is trapped in the surf zone, then, and it spreads in the alongshore, then the eventual fate of that fresh water will be determined by eddy activity. So in other words, that fresh water is trapped, spreads in the alongshore, and it'll eventually make it out onto the inner shelf through rip currents as an order 1 process. And then our fourth hypothesis for this work is that we will be able to model this, the wave-driven mixing of that fresh water in the surf zone using existing turbulence closure models. And I'm primarily focused on sort of the first and the third hypotheses in this work. My colleagues at University of Washington are doing the modeling, and then sort of all of us are working towards the goal of parameterizing this type of system. So our work builds on a few studies looking at small plume systems. However, studies quantifying river plumes are relatively few and far between. So this was an idealized modeling study as part of Angelica Rodriguez's PhD. She ran this coast simply. So we evaluate the wave momentum at the surf zone edge and the river momentum at the estuary mouth. And then using these relationships, we can see it leads to a relatively straightforward balance. This is a balance between wave momentum and river momentum. Okay, so this is one way to think about whether or not a plume will be trapped or escaped, using this balance of cross-shore momentum. And Angelica Rodriguez placed her model runs into a parameter space where we have that simplified momentum balance on the x-axis, and then we have a term on the y-axis, which is a what we're calling a freshwater fraction. So this is volume of freshwater in the surf zone over volume of freshwater on the inner shelf. So the gist here is that along the x-axis, we have this ratio between wave momentum and river. So as this ratio increases, it's indicating that more freshwater is being trapped in the surf zone. The three wave forcings from the model results that I showed previously are shown as these curves on this plot. And then there's sort of a rough cutoff for where there's a dominating river flux versus a dominating wave flux, which might tell us, if the plume will be making it out onto the shelf or will be entirely trapped. However, in this paper, Rodriguez wasn't able to formulate the x-axis so that the curves collapsed on themselves, which would enable to use this in a more predictive or functional term. However, after it was published, our colleague Gino Pollock worked to make an attempt to collapse these onto themselves. And to do this, he used a surf zone Froude number. So you can see we've now changed our x-axis, which allows these curves to collapse on themselves. So this has more of a functional form, which makes this a more useful parameter space for predictive capacity for placing other systems in this. So hold on to this. We'll be coming back to this Rodriguez parameter space later on as we try to place Lowe's pen into this system. The other parameter space that I will present is one done by Sam Kastner. He conducted this using observations at the Quinault River. So Rodriguez, this was based on idealized modeling. Now this parameter space is based on observations. So this system is relatively similar to Los Penasquitos. However, it does have a larger outflow from the river, so a stronger discharge, which you can expect. The Quinault is in Washington, and obviously my site is down in California. So to create his parameter space, Kastner looked at length scales. So instead of looking at momentum terms, we're going to actually do this using distances of three dominating parameters. So the first one is being a surf zone width. So this is simply the distance offshore of the edge of the surf zone. Then we have a length that predicts how far offshore the plume will go. So this is a LNF. It's like a near field plume length. And then we also have this in yellow, it's hard to see, this LC term is the length of a channel. So the idea is that if you have a wider surf zone, it will lead to more plume trapping. If you have a longer channel and it actually extends beyond the surf zone, it could funnel the fresh water out of the surf zone to create a plume. And then ultimately the length of that plume with relationship to the surf zone is determined by LNF. So these are the terms that go into it. LC and LSZ are measured. LNF is computed using a mouth velocity, a discharge, a G prime value from the river to the surf zone, and then this entrainment velocity term, which sort of comes out of a paper, Hetland 2010, which is the mixing at the base of the plume. And this is estimating using U0 and the depth at the river mouth. So this is the parameter space in Kastner's paper. So on the bottom axis, we have near field plume length, and on the y-axis, we have channel length, and they're both normalized by the width of the surf zone. So we end up with these sort of quadrants where everything to the left is going to be a wave-dominated system, which is indicating that the plume will be trapped in the surf zone, and everything to the right will be a river-dominated system, meaning the plume will make it out. And he found that the Quinault River tended to sit sort of, could have an escape, could have a trapping. but this is a much smaller system than, say, the Merrimack or the Columbia or the Fraser, where when you put those in this parameter space, we're always going to have a river dominance, meaning we're always going to have a plume escape. Okay, so let's get into our field work. Again, keep those in your back pocket. We're going to come back to those parameter spaces. So let's think about our experimental design for answering some of our questions. So the first question is, is the plume going to escape from the surf zone? And if so, our hypothesis is that that will happen when the river momentum is dominating. So this is a map of all of the instruments that we deployed for our field experiment. We released dye at the mouth of our estuary. We had a bunch of surf zone surf zone sensors, which had eco triplets, which measured the dye concentration, CTDs, and one of them had an ADV. And then we had additional moorings right at the edge of the surf zone, and then in deeper water in 8 meters. This is kind of demonstrating the drone footprint for an RGB drone that I used. I also used a hyperspectral drone, which we will get to, which is that's able to measure dye concentration remotely. And then there's a box here indicating transects that a jet ski was taken. So just a few sort of pictures from our deployment, the deeper moorings at 8 meters on the outer edge of the surf zone. And I forgot to mention, we actually had an even deeper mooring at 30 meters, but we never saw an instance in which the plume made it out that far. So these were deployed for roughly 2 months. The short-term deployments, the surf zone deployments, were only deployed for a 24-hour period during our collection. That's because there's a lot of surfers at this beach. And we also deployed these with a much higher sampling rate. So they only lasted for about 24 hours. But here's kind of indicating we actually deployed them at really low tide. So we could drill them into the sand. And then when the tide increased, you could see they were properly in the surf zone. I should say we also utilized drifters in this experiment. So these were developed by Matt Spidell. These are sort of, actually I have an old version of one, just a hydro flask with a GPS on it. And these were really helpful for deploying in the river mouth and then calculating outflow velocities. This is our jet ski. The jet ski had, as you can see in this image down here, it had both CTDs and eco triplets. Eco triplets are measuring dye concentration. They're fluorometers. And our jet ski driver here catching a wave. And then we had several drones and cameras. So we used 2 drones, one just a traditional DJI Phantom 4 Pro. This was capturing RGB imagery, which we mostly used for qualitative context. And then our drone also had a multispectral and a hyperspectral camera on it. The hyperspectral camera gives us enough bands, so enough wavelength bands of visible light that we're able to use the hyperspectral camera to calculate dye concentration remotely. And I'll talk a little bit about that later in my talk. So the dye released, we released on 3 different days. This was in January and February, right? So wintertime in San Diego, we were guaranteed to have some sort of outflow because there was a little bit of rainfall. So right, twice on each day. We did 2 releases on each day so that we could vary the tide without dramatically varying wave or river discharge conditions. So we did a higher tide release and sort of a mid-tide release. And on each of these days, we actually only released 7.5 gallons of dye. And I say only because when you see the images of the dye, you'll think it looks like a lot more. And we released that dye over the course of 20 minutes. And that dye essentially trickles out of the end of a tube that we placed in the river mouth, and we pumped with a constant flow rate. So this is one of the sort of context RGB images that I mentioned, and I'll just play this movie. You'll see what the dye releases looked like. Can I? Maybe? There it goes. So you'll see the dye starts getting released. And this is just very early dye release. And you see the jet ski is zooming around back there. Our drifter chasers are down here. Our drone station was set up right at the mouth here. This is where we're flying the drones from. So I'm going to show you snapshots from each of our 6 dye releases in the next slide that have images of essentially where that dye went on each of those days. So this is this is January, February, and this is the higher tide releases and the lower tide releases. So the summary of what we see, actually, I'll move to the next slide for this. These are rectified versions of those imagery. So now we're in real space. The summary of what we see is that on the February days, the plume was at the surf zone mouth. The plume was trapped for every single one of our dye releases. So you can see there is no river plume that has made it out of the surf zone. However, in 3 of the days, we had really strong rip current activity. And interestingly, often those rip currents were, within 100 meters of the mouth. So on this February day, there was a bathymetric channel just to the north, and this is a rip that is carrying that fresh water out. So it really does sort of beg the question, right? In the far field, does the inner shelf essentially care, so to speak, about the pathways of that dye or that fresh water, right? This the fresh water is making out of the surf zone in some capacity. What are the distinctions between a river dominated plume and a rip current? And then I'll just mention, so on the 20th, we actually did have sort of a wonderful escape. This is a river plume, a proper river plume escape, right? So dominated by river momentum. And what was pretty interesting about this escape is as it evolved over time, it had two things. It had some pulses in it. So it sort of created these mushroom heads, which we hypothesized was due to infragravity activity. We do have a grad student who's investigating that. But then also, once this fresh water makes it out of the surf zone, there is a small, but albeit present, G prime value. It's non-zero. And we believe that this plume is now out on the inner shelf behaving like a gravity current. And then on January 20th, the morning release, it was sort of this hybrid situation where there was a plume, but there was also trapped fresh water. So it was a hybrid trapped escaped. And I should say that on the first release, we also saw evidence of rip currents further down the shore. So there was trapped fresh water that propagated in the along shore in the surf zone, and then also made it out through a rip current. But on the second dye release with this large plume escape, no water was trapped in the surf zone. So it was entirely escaped out of the surf zone, and we did not see any evidence of dye-seeded rip currents down the coast. Okay, so this is a lot of numbers, but I want to present what we've done so far in testing how well our system fits into the existing parameter spaces that I've already presented. So we've estimated the non-dimensional parameters from both Castor and Rodriguez. And I guess sort of a spoiler alert is that they don't do a great job of predicting our system. So let's look a little bit more at the details. We have estimated mouth velocity, so this U-naught term, as the maximum along channel velocity using our drifters. We estimated Q using that U-naught value as well as the cross-sectional area of the river mouth. The significant wave height comes from buoys. We've computed an entrainment velocity using the maximum depth at the maximum outflow and U-naught. And I just want to take a moment here to point out that the entrainment velocity proposed in the Castor parameter space, so our values for this entrainment velocity are about an order of magnitude larger than Kastner's. And if we think about it, we have river water discharging into a surf zone that is very well mixed. So it fundamentally doesn't make a lot of sense that an entrainment velocity would apply when surf zone turbulence is order 1 mixing process, right? Remember, the entrainment velocity is that mixing along the base of the plume. Kastner actually found that there was stratification in the surf zone at the quinault. So entrainment velocity might be a more applicable parameter in that particular system. However, for the sake of applicability, we've attempted to calculate an entrainment velocity. We also calculated G prime. This is another tricky term. right? We first started our releases at high tide when the river was essentially still just discharging salty water. So G prime is very small. But on top of that, as an added complication, as the tide ebbs, G prime actually changes throughout the duration of dye release. So by the end of our dye release, the mouth has begun to discharge fresher water. So this means that we have a pretty small G prime, but it is, you know, there is a density difference nonetheless. Okay, so from these parameters, we can then compute an LNF value. And then, as I mentioned, LSZ and LC are measured using bathymetry. And what we find is that the trapping, the cases in which the plume was trapped are predicted just fine by Kastner and Rodriguez. However, they both predicted that our hybrid and our escape would also be trapped, which, as we've seen, were not. So just a quick sort of backtracking here, I just want to demonstrate how we calculated our surf zone width and channel lengths. These are brightest pixel images from our drone imagery, where I've sort of bolded the water depth where the depth limited braking would predict the edge of the surf zone. And then you can see the edge of the surf zone in the drone imagery for most of them is quite on point with that. So this is how we estimated surf zone width. And then the channel length is just the furthest offshore depth contour where the channel is no longer exists. And we can look at these in parameter space as well, right? You see in Kastner's parameter spaces, all of our dye releases show to be trapped, even though actually the blue one was a proper escape. And just thinking about the issues with Los Penasquitos, our lagoon, applying to this Kastner parameter space, I've sort of touched on these already, but our G prime is very small and varies throughout the dye release. We don't think an entrainment velocity is necessarily applicable, so we sort of need to come up with a way to remove that term. And also our bathymetry is very important. This does not incorporate changing mouth bathymetry. Actually, I think I took out this slide, but I should say that the second dye release had an angle to the channel, and so that is also introducing an alongshore component to the flow. Also, the presence of any shoal as the tide recedes at the sort of the end of ebb tide, we see the fresh water is sort of just trickling over the swash zone at that point. So we no longer have this proper river entering into a surf zone. And then also, as I mentioned, it's very difficult to estimate the mouth velocity and the discharge. Okay, so in Rodriguez, we sort of have the same problem. We see, you know, there's trapped fresh water for most of the dye releases, but then, so it's sort of mostly trapped, but then for our actual plume escape that we observed, we're predicting 100% trapped. And again, that's not what happened. But the Rodriguez parameter space only considers wave height and discharge. And so there's clearly terms that are not existing. So to summarize this parameter space fitting, what are we missing from these idealized perspectives that prevent Los Pen from fitting into them? I've bolded the ones that seem most important. First one being presence of any alongshore currents. Second one being bathymetric steering by the mouth of the estuary. General morphology, which has a tendency to change very rapidly. Also, tides are not implicitly considered in these parameter spaces. And then a few other complicating factors in this type of system: rip currents, internal tides, submesoscale fronts. And then it's also difficult to, in general, right? I said we used drifters to measure our mouth velocity and discharge, but these are difficult to measure in a predictive capability, right? If I want to know, say, as someone who works for, you know, civil works, if I want to know what conditions lead to trappings and escapes, I'm not going to be able to have drifter measurements for, you know, every scenario. We're going to have, say, an upstream gauge discharge value that we need to apply downstream. So we're sort of we are in the process of trying to fit Los Pen into a new parameter space. And one thing I've been working on that I'm not going to show because it's still a work in progress is incorporating a longshore component of outflow velocity that's due to an angle of the mouth channel. So that's sort of one hypothesis that we have that may improve these. Okay, so I want to move on to my sort of next hypothesis, and that is if that fresh water is trapped in the surf zone and starts spreading in the alongshore, we hypothesize that it'll eventually make its way out of the surf zone through eddy activity. So our schematic for sampling the system, here I'm showing you river outflow. Moorings are indicated in yellow. And then I want to think about the system as somewhat of a control box, a control volume. So at the edge of the surf zone, we could have a jet that is the initial plume outflow. We also have freshwater leaving the surf zone through the presence of eddy activity and possible dissipation. And then we have the alongshore boundaries that we have to draw for sampling purposes where the freshwater is leaving that direction. So to sample this control volume, we will use the jet ski and the hyperspectral imagery. And it requires that we sample both the outer edge of the control volume as well as the alongshore edges of the control volume. So the jet ski can sample in deep water, no problem. And the jet ski can also take cross-shore transects driving sort of in and out of the surf zone. But it can't do any alongshore transects in the surf zone or come too far into the surf zone. So the jet ski alone is clearly not going to help us solve this control volume. These are just some sample jet ski paths that we had to sort of pre-plan before the field experiments. This was a medium size box oriented towards the north or symmetric or southward. So just getting at our experimental design. So as I mentioned, we're not covering all the edges of the control volume. However, the hyperspectral drone can fly wherever it wants. So the hyperspectral drone, which as I mentioned, also is able to calculate dye concentration, can do alongshore transects in the surf zone as well as the outer edge of the surf zone. Our only limitation here is that we can't fly it too far away from the pilot. So let's talk a little bit about this technology of the hyperspectral drone. So a typical RGB camera records 3 different wavelengths. We record red, green, and blue. And then to create a composite image, those sort of 3 different wavelengths are meshed on top of each other. This is called a Bayer pattern, and that gives us an image that looks like the world that we see. However, and so then a multispectral camera, as the name would suggest, is now more bands. So let's say we've added an IR band, we have our red, green, blue, and we also might have, an additional band thrown on top of that. A hyperspectral, on the other case, is able to record 300, so our particular camera records 300 spectral bands. So this is 100 times more bands than what an RGB would record. And you can see in this plot, we're essentially taking the entire visible light spectrum and discretizing it into 2 millimeter bands. So we can distinguish between something that's, red and a rusty red and a little bit less red, very, very clear distinctions between different wavelengths. So these are the 2 cameras that we use. I'm going to focus on talking about the hyperspectral band. The operation, this is our particular camera I'm just showing you. We mounted it on a DJI Matrice hexacopter. This is quite a big drone. And the sample pattern of the drone is a little interesting. It's called a push broom camera. So it essentially collects a single row of pixels over space. And sort of the reason why that's important is because it dictates our sample ability, right? We have to be looking straight down at the water. We can't be looking obliquely at a large region such as we might be able to with an RGB camera. So this is showing, right, a 640 pixel wide band collected over time. And how that ends up looking is we have, for a given timestamp, we have 273 spectral bands over a 640 pixel wide snapshot. And something a little bit quirky about these cameras as well is if you take your phone and you want to focus on something, you can tap on the screen and it can adjust how it's imaging in real time, we have to set the exposure manually before takeoff. So we're essentially pointing the camera at a white card and then manually telling it the exposure based on how much light, how much sunlight is out that day. So a little bit more complicated of a sampling than an RGB drone. Now, the use of hyperspectral cameras for dye measurement is not new. This is an image taken from, sorry, this is a camera that was mounted on a airplane. This is a hyperspectral camera, very similar to the one we used. And then in a study in, this was done in 2017, I think. This is from a paper Derek Grimes published. This is called the Seaside Experiment, where they were studying rip current activity using dye as well. They successfully measured dye concentration on the inner shelf. However, using the plane could not get high enough resolution to estimate dye concentrations in the surf zone. The reason being is that that rolling shutter that I showed with that push broom approach, a plane has to fly a certain speed in order to, essentially not fall out of the sky. And so those snapshots were taken with quite a bit of spacing in between them. So the resolution was not high enough to get anything quantitative out of the surf zone. But this is sort of where we are able to step in with the drone approach. So how the dye is, the concentration is estimated, what we do is take a ratio between the emission wavelength of the dye and the absorption wavelength of the dye. So we can distinguish between essentially the dye's excitation and the dye's absorption. So we see in this example spectrum, we have a peak in dye and then a trough in dye at those two bands. So we take a ratio of the intensity at the emission band and the absorption band. We call that a dye intensity value. And then using our recorded dye intensities and a whole bunch of in situ overlap, we can calibrate the dye intensity to dye concentration. So this is an example of what our curve fit looks like. We would have our in situ data and our intensity values and fit a curve to those. These are some examples of how this was computed in a paper by Dave Clark. And then again, showing the Grimes plot, not able to be done in the surf zone yet. But I'm getting to that with ours. So this is kind of an example of some observations. Starting first, so you kind of know what we're looking at. This is a video of a rip current to the north of the mouth. And then when we look at the hyperspectral transects that we took, you see I'm plotting the red, green, and blue bands. So what we think an RGB image would look like just from the hyperspectral imagery. And you can see we have this dye water, this plume to the north of the mouth. And it evolves over time. So in our sample strategy, we did these boxes repeated over time. So we can not only get some spatial information, but also dye change over time. And then to compute the actual dye concentration, we did a number of these flights after the dye release, sort of towards the end of the dye releases, where we had the jet ski look up at the drone and follow the drone. So we got an overlapping data set between the jet ski and the drone. And that gives us hundreds of data points which we can calibrate to. And these are some example spectra from our data set. So you can see very clearly in the dye water, there is this strong trough at the absorption wavelength of the dye and this strong emission peak at the emission wavelength of the dye. And then again, using this intensity value and all of our overlapping data, we can calibrate to dye concentration. So this is an example of dye concentration that I've estimated. So here we have the RGB imagery from the hyperspectral drone. And then on the right, we have dye concentration from the hyperspectral drone. And what's great here is you're seeing we have concentrations computed in the surf zone. And then just to sort of show how these two data sets are meshed, we have the jet ski transect showing coming in and out of the surf zone. So for to look at this quantitatively, for each of the dye releases, we've defined boxes where we have the edge of the surf zone, we have the, and then we have the shoreline. And I've done this again using the brightest pixel images from the RGB camera. And we create these boxes of inside of the surf zone and outside of the surf zone or on the inner shelf. And when we look at all of the data points from both from all 6 dye releases, both in the surf zone and on the inner shelf, you can see we have this sort of characteristic time scale over which the dye concentration in the surf zone is starting to decrease, and the dye concentration out on the inner shelf is increasing. So this is still a work in progress, but so far what we've shown is that there is a predictable time frame over which we will start to see that, essentially fresh water making it out of the surf zone, and how long that process takes. Okay, so I'm sort of wrapping up here. The key points that I want to make from this talk are that our plume fate, both in and out of the surf zone, was observed on 6 different dye releases with comparison to 2 existing parameter spaces. However, it's a slightly different system than the 2 that have been previously studied. So we need an alternative parameter to describe this system. Our remotely sensed dye concentration has been estimated both inside and out of the surf zone, which is great. And from our remote and in situ measurements, we can see that there is a trend of timeframes for which dye is leaving the surf zone. Next steps is taking those hyperspectral and jet ski concentrations in and out of the surf zone. And I'm proposing for sort of a next step analysis, integrating for a time series, integrating in space and time for each of those to essentially get like characteristic concentrations both in and out. And then on top of that, since I mentioned we have these time series of boxes over individual plumes and rip currents, we can look at the time evolution to get a prediction for essentially spreading rates and dissipation rates. And then really quickly, I haven't touched on this too much, but I thought I'd mention some of our other data flows. We had a multispectral camera on the Matrice as well. So this camera was also down looking, and it also had a thermal sensor on it. So I've have this data set for potential use of thermal imagery as well. These are some snapshots that were taken from the RGB sensor on the thermal camera. This is kind of just for aesthetic. But then when you look at the thermal camera, we're starting to see that there are distinctions in the plume water and the surf zone water where we might be able to do something quantitative with this. And I want to finish with this video. If you're prone to seasickness, I would watch with caution, but this was kind of a nice video that was collected during our field campaign. And this is of the large plume escape. And what I think is interesting is as the wave breaks, you can see, you can get an indication for how thin the plume is, because you can see as that water mixes up behind the wave, it does not have dye in it. So we think this is like quite a thin plume. All right, and with that, I will take any questions.
Thank you very much, Alex. That was really educative. I really enjoyed the talk, but I'll open the questions for the floor. Any questions?
I have a question.
Josie, go ahead.
Hi, so instead of using dye, if you had a sediment plume coming out of your river, could you have modified your techniques but followed that process instead?
Yeah, so a couple of thoughts on that. I have a colleague who has studied the Russian river plume and has been able to see it in satellite data. So he's been able to use different bands with satellite data to sort of give like a, yes or no plume presence. Our system is too small to be observed with satellite data, but the ability for a hyperspectral to distinguish between turbidity is something that hasn't been proven yet. Mm-hmm. So I'm actually interested in that from like a broader perspective. Now that I'm at the Army Corps, we're interested in dredging activity, things like that. But using the hyperspectral to say something quantitative about the amount of turbidity is still not quite possible. If it were distinguishable enough, you could do like a qualitative look at, you know, plume size and all of that. But again, it's still going to be too small to show up in something as broad as a satellite. So.
Right. Well, thank you. Very
Yeah.
interesting talk. Enjoyed it.
Thank you.
Okay. Bob, you have a question?
Yes, thank you for that very nice talk. I'm wondering how you treated the bottom boundary condition, particularly in the surf zone. And given that sand's highly permeable and you have bulk flow through it, and whether the mass balance of your dye introduction would be affected by a permeable bottom and advective flow through it. How did you actually deal with that?
Yeah, so the permeability of the bottom is definitely like within our error margin. So we're not considering something as, you know, as a term as small as that. But I will say that we are making the assumption that the surf zone is well mixed. So the dye is completely mixed through the surf zone. And then when it makes it out of the surf zone, we have to estimate a plume depth. So our bottom boundary condition for the plume layer, we've estimated the plume is less than 1 meter. So that's determining sort of our, you know, inner shelf third dimension, and then our surf zone, our bottom boundary is, we're just treating it as a rigid bottom and assuming it's well mixed. So,
Okay. Thank
yeah.
you. Thank you.
Thanks.
Jack is next.
Hey Alex, that was an awesome talk. Really cool to see the different data sets come together here. I'm wondering if you can talk a little bit more. I know you mentioned a few times here at the end, especially the thinness of the plume, but I want to go back to your hint earlier about like, does the inner shelf care whether it's an escaped plume versus like a rip current? Can you comment on where you're at, like what your initial thoughts are on that? And then also, you know, that thin plume, do you think that's I know you only had one escaped case here, or one hybrid and escape plus real escape. Do you think that that's a representative sort of example? Like, do you think it's always thin in the escaped case? So anyways, I'd love to hear your thoughts.
Yeah, totally. So there's two directions we can look at this from, right? We can look at the inner shelf sort of bulk freshwater characteristics. And we do have a grad student who's looking at sort of far field effects of plumes. I should say that these dye releases were not done on the highest discharge days that this plume can see. So there are instances in which there's a much larger plume that makes it down south to where the Scripps Pier is during like, you know, short storm events. So these were sort of like, I'd say mid-scale plumes. So yeah, so we're looking out from the inner shelf. I don't think, you know, at the end of the day that when we're looking out at that outer boundary condition, the fate of the freshwater sort of matters where it came from. It's still making out of the shelf, out of the surf zone in some capacity. However, if we're thinking about it from the beach, from the perspective of a beach goer, we care if that fresh water is making it immediately out of the surf zone right at the plume location, or if we have, or I should say river location, or if we have this alongshore spreading before it makes it out of the surf zone, then we have to be concerned about pollution and nutrients in the surf zone for beach goers. So the trapping versus escaped is more of a near field concern, but still like a very relevant one to nearshore activities. And then the sort of analysis that I'm working on now is distinguishing between the dye concentrations for the escaped plume versus a temporally consistent rip current. And I'm finding that the plume concentration is higher than a rip current concentration, which makes sense because that fresh water has mixed in the surf zone before it has made it out as a rip current. So the plume dynamics of, you know, an initial jet escape versus a rip current escape are going to be a little bit different. They're going to have different G primes, but ultimately, right, the fresh water will make it out. And I should give a little shout out to the PhD student working on this project from University of Washington is doing, his name is Yingzhong Liu. He's doing some really fantastic idealized modeling where he's also considering the alongshore extent that freshwater goes. So that can kind of also give like, north-south bounds for where we expect to see freshwater as well. We couldn't sample far enough to actually find the boundary in the surf zone, but he's finding like on the order of kilometers in his idealized cases. So that's kind of another like boundary on that. And then you asked about the plume thickness. Yeah, we don't have the capacity to measure that because it is so thin, and our sensors were already at 0.5 meter and 1.5 meters. And so distinguishing between those where the plume lies was, we would have needed probably an acoustic sensor or something like that, which we weren't using. So yeah, hope that helps.
Thank you. Minghua, you have a question.
The escape second release on January 20th is very different. You mentioned the gravity current. What makes with gravity current, why this one has gravity?
Yes. Oh. Yeah, so the reason that one, would behave like a gravity current is only because it's has actually escaped out of the surf zone. And so similarly, we hypothesized that a freshwater seeded rip current, we already have our dynamic complications of a rip current, but then you add buoyancy to that problem. We hypothesize that it will behave with some buoyancy driven flow. But everybody has asked me this at Ocean Sciences, and this week, the one distinguishing factor that tells us why that one was an escape is very difficult to put our finger on. So like, why did that particular one escape? There was a ripping velocity. So the velocities were very fast. And the fact that the second plume escaped so much more dominantly than the first plume has to do with the fact that the tide level has decreased. It has changed our mouth cross-sectional area, and also our sort of dA to dt has increased. So there's more of a tidal component to that outflow velocity. So if you look at the velocity term that we've calculated from our drifters, baked into that velocity term, it's quite a bit higher of an outflow, but based into that velocity term is a tidal component, a morphology component, and then there was a small change in wave height and a small change in river discharge. So it's there's kind of this confluence of factors that we're teasing apart.
Thank you.
Steve, please ask your question.
Yeah, hi. Just compliment you on so many aspects of this work, just from the putting the team together and getting all these measurements, the ability to use the hyperspectral with the ratio to get the concentration, the ability to parameterize this thing is just all impressive. Sort of a question is, how long does it take your push broom to take the photograph? Another question, totally different, is what kind of permitting did you have to get to put all this together, including the dye release and all the flying equipment?
Yeah, the second question is a funny one. It's a lot of permits, and we decided to do this in a state park at one of the most populated beaches in Southern California. So, we had a few challenges, mostly more along the lines of like, not in my backyard type things. But we actually had the reason we have all these nice photos, actually, we had a pretty strong communications team. And so our comms team, Scripps has, a great comms team, and they sort of got out in front of any concerning questions people might have by having, descriptions of the dye indicating that it's non-toxic, very clearly stating what we were doing, prepared, so that when people saw, biking down the road or hiking, see the dye, and are concerned for environmental safety, things like that. Those questions were already like available for them to kind of look into. So I think like the permitting and the day of concerns from beachgoers was definitely a challenge. I think we needed like, I want to say we needed 6 permits from 6 different agencies. It was kind of outrageous. And then your first question with the push broom sensor, I want to say that the timestamp for every single row was, you know, a couple milliseconds. Is quite fast. I can tell you that the speed, so the speed of flying the drone becomes a very important parameter in sort of how we're sampling. So here, I'll give you a little, this is kind of an interesting tidbit. In lower light conditions, we have to collect each row a little bit slower so we can have the exposure open for longer and collect more light, which means we have to fly slower to get continuous timestamps. In higher light conditions, we can fly a lot faster because with every individual timestamp, we have a much faster exposure. So there's the, so I should go back and say the absolute speed of each frame is dependent on our exposure, which is dependent on the lighting conditions. So.
Oh, okay, thank you for that. Yeah.
Yeah, I'm happy to talk more about the technical details if you'd like.
The RGB can do it a lot quicker.
Yeah.
But as you point out, you get a lot more information from the hyperspectral.
Yeah, a lot more information, but at the cost of, you know, a bit of a complicated unit. So, but yeah.
Thank you.
Okay, Mohammed has a question. Mohammed, go ahead.
Yeah, thank you for enchanting presentation. I am wondering about the density of the river bloom factor. If it will affect your hypothesis, like if you have like a different type of river bloom densities, how it will work with your hypothesis.
Could you repeat the first part of the question?
Yeah, just like I am wondering about if you have like a different bloom with a variety of densities, how it will affect your hypothesis.
Yeah, no, I think a lot. So the idea is we're trying to come up with something that is somewhat universal to similar systems. And the different systems, the parameters that we've looked at as sort of order 1 factors are right, the discharge and the wave conditions and the bathymetry. In terms of density itself, that's an interesting point because in our system, as I mentioned, the density distinction between the plume and the surf zone was very minimal at the early phase of the plume outflow. And so the density, the G prime changes throughout a tidal cycle. But in terms of like, if that's a noticeable parameter in other systems, yeah, I'm not too sure. You know, I could see there, yeah, I'm actually not too sure if like besides the tidal influences of estuarine mixing, I think that would be like, you know, parameterizable in other systems as well, because we know, you know, discharge rates and tide and things like that. So I'm not sure if that answered your question or not, but.
I think it did address it. Thank you. So I have 2 questions for you. In one of the factors you mentioned was it was not important, but it was of interest to me. It was the internal tide. But I'm wondering how much of an influence internal tide is going to be in the surf zone, and why did you consider that? And the second question is on the dye intensity when you are using the hyperspectral camera, because you took the difference, the ratio of it was the absorption and the emission, right? And I wonder why you did not normalize it, because as time goes, the concentration of the dye is kind of waning. And so if you don't normalize, you might not be getting one and the same thing, but maybe you did consider and found it was, I just want to know your thoughts about that.
Yeah, so the internal wave question, internal tide question, yeah, I agree with you. It's not it's not going to be a super important parameter in this small of a system. Infragravity energy will have an influence. Like I mentioned, we saw that plume pulsing. But I guess in terms of, I mean, I guess there's sort of downstream effects of nearshore mixing that is induced by the internal waves, but not something that we're immediately trying to incorporate in this at all. And then with the dye intensity, so the intensity value is incorporating the fact that the concentration is waning, because as the actual dye concentration decreases, that recorded dye intensity should be giving you a lower value. So we're normalized. The only thing we're computing is the ratio between the absorption, I should say, yeah, the emission and the absorption, and that's going to decrease as there is less concentration existing. So we don't want to normalize it because we want to be able to distinguish between the intensity variabilities as the dye concentration changes.
Okay. Okay. Thank you very much. And I don't see any questions from the floor, but Steve wants to make a comment. Okay, Steve.
Yeah, just a quick additional comment. The fact that you've got this 20-minute release really averages over that sort of period of time. So maybe high time resolution is not all that important.
Sorry, what time resolution?
So maybe if you got a 20-minute release, that spreads things out over time. So maybe a high time resolution in the observations is not so important.
Yeah, I will say, like, we're definitely not setting up a steady state plume. So in the idealized modeling, we can force dye release for a couple hours and sort of set up this steady state system. But there's an inherent temporal variability just due to the fact that the dye itself is sort of dissipating. But yeah, I agree with you. I mean, I think we're thinking on the order of like minutes, not on the order of seconds, maybe on the order of tens of minutes. So, yeah.
Yeah, I think that makes sense. And there's no way you could get a steady state because you got the tide changing on you.
Yeah.
Can I ask one last question, Alex? How long does it take to completely be unable to see dye?
In the near field region that we are sensing, to get the dye below the noise floor of our instruments was about 3 hours. And that was about the time frame from the first release to the second release. So we're not expecting, like, in the second release to still be recording things from the first release. Sarah has sort of mentioned, in theory, it's like detectable, for longer than that, but it's moved out of our region by the time we put more dye into that close range region. But yeah, that's a good question. Yeah. This was a great discussion. I really appreciate it.
Yeah, thank you. Thank you very much. It was a very nice talk. Enjoyed that, Alex. Thank you.
Yeah, thank you. I appreciate it.
Thank you, everybody.